Aloha kako. I think there's been a good primer on the longline fishery, so that's a bit helpful for context of this talk. I do want to give a big mahalo to my co-authors, which I'll do again at the end, but let's kind of jump right into it. So for those of you who are not familiar by now, the Hawaii longline fishery is Hawaii's most economically valuable fishery, and it's really divided into two sectors. So you have a shallow set longline fishery targeting swordfish. That's largely fish that wind up going to the continent. And then a deep set ahi fishery that's mostly going towards fresh fish here in Hawaii Pai'aina. And these two fisheries have separate regulations and separate gear types and timings. So the shallow set fishery, which is going to be on this side, we can see the swordfish. So I guess your left. You can see they have the moon phase above that set, indicating they're fishing at night. They're also fishing at about 50 meters water depth, so pretty constricted in the vertical range. And then on the right, you have the deep set ahi fishery that can nominally be a daytime fishery, but they really fish an incredible amount of the day. A lot of sets are averaging nearly 20 hours of operation. So it really is crossing from day and night at this point in time. But in terms of fresh island ahi that you're likely getting in poke, it's mostly coming from that fishery. And the Pai'aina here is located in the subtropical gyre of the North Pacific, but these fisheries have huge footprints. So the deep set longline fishery covers most of this gyre, as you can see here by this kind of cartoon diagram here in green. And then the shallow set fishery that's targeting swordfish is really going for that subtropical front between the subtropical gyre and the subpolar gyre. So some of the reasons to study this fishery, beyond the fact that it's tasty fish that we like to focus on and its economic value, are the bycatch concerns and the non-targets that this fishery interacts with. So it's a really well-managed fishery by international standards. It's one of the most regulated fisheries in terms of longlines, but it has had issues with bycatch in the past. So this includes sea turtles and seabirds. So things like moli and kaupu, so these are the laysan and black-footed albatross, and then sea turtles such as loggerhead and leatherback. Those particularly for the shallow set. But it also catches a number of other valuable species beyond just ahi and swordfish. And so a natural question, at least for me, was trying to understand what particularly about oceanography and some gear selections lead to variability in the catch rates of this large suite of species. So I'm going to be focusing largely on the targets and secondary targets for this talk, but happy to talk about those hot button species if you're curious later. And the way this is done is through species distribution modeling. It's really a form of catch rate modeling because we're observing these species occurrence and abundance through the fishery, not through fishery independent data or tagging. But really matching those fishery data to environmental signals to generate spatiotemporal output of predictions of occurrence or catch rates. So here in this far right panel, we could see OPA. This is a probability of occurrence on a set here, and you can see how it's kind of moving through space and time on a monthly scale. The data sources that go into these models come from the Pacific Island Regional Observer Program. So this is really a fantastic data source that we often really rely on, especially for pelagic fisheries data. So whether it's the ecosystem type science that I focused on in the program I was formerly in, or the fisheries research and monitoring program that has to understand different things about the stock assessment and stock status for these individual species, this observer program is really key. The shallow set, it has 100% coverage, and for the deep set, about 20% coverage. And then we have two slightly different time scales in terms of what temporal coverage I'll be focusing on in these models. That has to do with some closures in the fisheries. But overall, I just want to highlight these are really large data sets. So you have 20,000-ish sets in the shallow set that I'm using and about 70,000 in the deep set. A couple of brief definitions that I'll use throughout the rest of the talk. You have catch rate, so this is fish individuals per 1,000 hooks, or CPUE, and then interaction probability. So this is the probability of occurrence on a given set. The way we say interaction probability is because, again, it's not a true presence-absence of that species that has to be caught in order to be observed. The environmental data sets that go into this come from a variety of sources. We have used remote sensing for a lot of those surface variables, but then we also pair with some hydrodynamic model output for both subsurface variables and things that the surface, that remote sensing does not cover very well. So things even like sea surface salinity, where satellites don't tend to do an awesome job. We kind of use these hydrodynamic models to help fill in those gaps. We also have a variety of other sources. I won't talk about eddies much in this talk, but we do include that to try to see if that has an effect based on past work, and then things like day of year and lunar cycle. Modeling technique here is, we're calling ensemble boosted regression trees, but it's really a form of machine learning. This is very different than maybe some of the AI you've heard earlier. This is something you could do on your personal laptop. It's not that complicated. We call it pretty interpretable machine learning, especially how this is developed. But it's really a way to try to get high skill at low interaction rates, so for rare occurrences, and also decent skill in terms of catch rates for the species we want to focus on. And then the ultimate, what we're using here is a delta log normal, so a multiplicative result of the occurrence process and then the abundance process. Because basically these models do require statistical distribution to optimize their formation, and Tweety is not really an option here, hence the delta log normal. So the next section of the talk, I'm really going to focus on the shallow set fishery. So this is the one targeting swordfish up at the subtropical front. A lot of text here in this diagram, but I really just wanted to focus on those last couple of columns on the right. So first off, you can see all the individual species that this fishery is regularly interacting with, ordered in terms of how often they're actually caught. One obvious one, if you look at the top, is swordfish or auku or shitome, if you see it in the markets. They catch it on almost every set. So there's no absent process pretty much. They're pretty good at finding swordfish, which is intuitive. That's what they're going for. But on those far two right columns, you have the AUC, which is, you can think of this as like a grade in school. So this is basically how well the model's performing in terms of its ability to predict occurrences that the model has not seen. So this is on test set data. And it's generally above 0.8 and almost always above 0.7. I think each individual model here actually is above 0.7. They're all passing models in terms of their ability to predict whether or not interaction is likely to occur for a given species. The second column is R squared. This is more interpretable for most folks. So basically, how good is it at actually estimating how many individuals of that species are going to be caught? This is a harder lift for the models, and you'll see a lot more variability here. So high R squareds for the frequently caught species and a number of other ones. But we do have some weaker models around 0.1 or 0.2 for things like hebi, which is short bill spearfish. But again, I think we have pretty good skill, especially in the target species, and that's really what we're worried about if we're going to think about bycatch concerns. Perhaps what's more academically interesting, at least to me, is to understanding why those models work, not just that they work. So here is the vertical axis, are all those individual species again. And then the horizontal axis is the suite of predictors that are used in these models. So an obvious one that jumps out is those big bubbles, and that represents how important that predictor is for that species, is the permit number. So this is Captain effects. These Captain effects represent a few different things. It's a little bit of spatiotemporal autocorrelation, but it also has a lot of things that we just don't observe clearly in the observer program that might be affecting catch rates. This has been shown in a number of other studies of fishers basically fishing in the same time and space, and due to small different techniques catching vastly different things. But if we look at what's actually going on in the ocean state or the oceanographic variables in terms of driving the catch rates, this is what this plot would really focus on here. So now we have a different wrinkle to this, is the color of those bubbles. And the color represents where over that parameter space that species has the highest catch rate. So we focus on Nairagi or striped marlin. You can see that red dot there. It's both quite large and, again, warm. So you can see that they're actually caught at the highest rates at the upper end of the sea surface temperature that the fishery interacts with. Again, this is a shallow set, so they're not fishing in the warmest of waters. So they're actually caught at the highest sea surface temperature that the shallow set fishes over. And that's what this plot shows here. And that vertical axis is just basically the standardized localized effect for that individual predictor on the catch rate. For blue shark and mako shark, now moving over to chlorophyll, you can see they're caught in areas with just higher chlorophyll concentrations. So similar to that cooler, more productive water canonically. And then this is where at least I think it gets a little more interesting. You look at sea surface salinity. And this might not be a super intuitive variable for most folks as to why sea surface salinity might matter. But it does indeed play a large role for a lot of species. You can see it's actually the second most important ocean state variable in these models. And the reason is because it kind of partitions the fishing grounds. So here we have this ellipse is basically the cartoonish diagram of where the fishery operates. On the top panel, you have sea surface temperature. And that black line is the 20-degree isotherm, kind of what we think of as the subtropical front. And then on the bottom, that black line is the 33.5 isohaline. And what you notice is that they don't have the same angle. The isotherm flattens as you move from east to west, but the isohaline does not. So what it allows you to do is parse individuals that have high catch rates in cool water but are just out west versus species that are caught in cool water but close to the Eastern Pacific upwelling zone. And that's what this biplot does here. It gives kind of a depiction of where these species tend to be caught the most. So we have species caught south of the transition zone, kind of near Hawaii in the subtropical gyre. This is that warmer, salty water. As you move north, you can think of this as water getting cooler and typically more productive. But then that kind of east-west component, moving from left to right, is species caught at higher rates outside of that Eastern Pacific upwelling influence, and those caught closer to the California current. And one of the things that is commonly used by physical oceanographers to deal with the compensatory density effects of water being warm and salty or cool and fresh is a term called spiciness. So think of warm salty water as spicy, cool fresh water as minty. And it's really a way to kind of collapse these two variables into a single metric that's useful. And so if you were to plot where the catch rate, this is the interaction rate, peaks for all these species in that spiciness metric, you could see a very similar kind of pattern that I just showed you. All these species in the bottom left here are those in that relatively minty water, so closer to the California current. As you get toward the transition zone, it steepens rapidly, and then you have the species caught in the spicy water, which is the warmer, saltier stuff. So things like aku, hebi, things you classically associate with near Hawaii. Notice swordfish was not on there because that's for the presence absence. But if you look at for the abundance portion, you can see now we have swordfish here, similar plot for most species. But swordfish is right in the middle, which I think is kind of useful for thinking about why you get so many different kinds of bycatch in this fishery, because the target species kind of sits right in the middle of this range. Next quick component I'm going to show is looking at how these catch rates vary in space and time. So the warmer colors in this diagram represent areas with higher catch rates, cooler, lower estimated catch rates from the model, and then fishing effort in the shallow set on the horizontal axis will move across. You'll see generally there's more warm colors in the winter when the fishery is operating at the highest. This is intuitive. This is generally the fisheries fishing when the fishing is best. When we look at a commonly bycaught species, the mako shark, we actually see a similar pattern. You can actually also see that top right corner is that cooler, fresher water that has the really highest catch rate there for that species. And we're going to move on to nairagi, which is striped marlin, a species of concern. And you can see the exact opposite pattern. It's not a super high bycatch species in this fishery, but it does occur fairly regularly. But it actually has higher catch rates in the warmer months in the summer. And if you collapse that over into 2 dimensions, it looks something like this, where you have the collocation or spatial correlation with the target, swordfish, and then mako shark in orange and striped marlin in blue. What you can see is generally those warmer colors means higher, mako shark is higher up, so higher collocation with the target, harder to avoid bycatch. Striped marlin, it varies throughout the year. So there's going to be times a year where you can catch swordfish and not striped marlin. I know I have a couple minutes left, but I'm going to show a quick slide from the deep set to kind of get you excited. This portion of the work is a lot more preliminary. But again, we're now focusing on this deep set ahi fishery. I'm going to jump right into the drivers because I think it's interesting in terms of a comparison of catch rates. So you'll notice a very similar suite of species on the vertical axis and a slightly different set of predictors on the horizontal. But what I really wanted to focus on here, and another quick thing you'll notice, is you'll see depth layers, because this fishery has hooks that go from 50 to 300. So now we have to using more subsurface variables. 2 things to focus on are oxygen at 300 and temperature at 150. That's because they kind of create a nice bowl shape in the gyre where the fishery operates. So temperature at 150 is cooler north and south of the archipelago, whereas dissolved oxygen at 300 has a really steep south to north gradient. So if you plot peak catch rates in this fishery on this biplot, you could see kind of different quadrants forming. Those caught in the southern portion of the gyre, where it's relatively warm subsurface but low dissolved oxygen. Those in the central of the gyre, warm but high subsurface dissolved oxygen. And then those caught in the kind of north-central area, where high subsurface dissolved oxygen but cooler subsurface temperature. And so with that, I'm going to wrap up. We were able to recreate the catch rates well for species in both of these fisheries. I really focused mostly on the shallow set, but we were able to do pretty well in both fisheries. The surface variables are really important for partitioning catch rates in the shallow set, whereas subsurface variables play a really important role in the deep set, fairly intuitively. And then these are really serving as a foundation for us to start to look at how climate change might ultimately affect these catch rates and bycatch rates as we move into the future. That, I'd like to give a big mahalo to all the co-authors, CIMAR and CEFI, for funding this, and leave up for any conclusions.